Okay, guys, I have an equation for the vibrational frequency of an equilateral tetrahedron, and I also did a similar estimate regarding the Great Pyramid of Giza, which I know a lot of people are interested in, and I'll put that at the end of the video. But let's keep going with the three-sided, more simple equilateral pyramid. This is the equation that proved out to be close. I mean, real close. And I came up with this really, honestly, with a lot of guesswork, combined with former knowledge. So pretty much what we've got here is a combination of Hooke's law, which is the basic vibrational frequency equation. And then you've got Poisson's ratio, which is a ratio of lateral strain to longitudinal strain. It has to do with how the material moves and strains and stretches. I'm a little weak on that one, but that's okay. Longitudinal velocity of sound in solids, we're going to call that velocity of a longitudinal fashion. Remember, there's longitudinal, which is like a shockwave going through a material, and then transverse, which is like a guitar string sort of wobbling in the air. So there's different modes of vibration, and we're going with the longitudinal mode for these brittle substances like limestone or metal or what have you. So the this equation, I had the computer do it, cut some time out, and we're getting 6420 to 6451 meters per second for the speed of sound in aluminum. So my equation here is actually not super complicated. It's the speed of sound, the longitudinal speed of sound in the material divided by 2 pi. And then this is the part that I just kind of threw together and it seemed to stick. 4/3 times the distance of the side of the pyramid divided by the square root of 6. Well, that works only for a 3-sided. There's another one for a 4-sided, 8-sided, etc. But this one's specific to the 3-sided pyramid, and it was only proven at one scale size. I did 60 test runs, but we'll get to that in a minute. But yeah, it comes out to a frequency of 12,118 hertz when I crunch the numbers. And I took painstaking data after casting a solid aluminum model of it and labeling it. I first started with this, and the mold didn't come out very good. So I made a bigger mold, used sand mold, and melted down this aluminum and created this pyramid and then labeled it. And then I started whopping it with a hammer while throwing it into the air so that it would ring, And so what that kind of sounds like is like this, right? All right, let's see. I don't know if you can see me, but basically we take the hammer and we pick one of the corners and then here we go. Oh, not a very good one. Let's try again. There it is. You heard that ring? Now I know you might be thinking, oh, shoot, it's the hammer, dudes. No, anything you whap it with, if you whap it hard enough, it'll ring. All right, so it's the same frequency, and man, I told you I was on a roll tonight with this stuff. So I painstakingly went through each corner, each side of each corner, and recorded the data. Each time I'm getting these numbers and a secondary higher frequency that kind of wiggles around more. I don't know. That could be due to irregularities in the metal, probably, maybe. But just going with this right here, look how consistent I'm getting. And the 188 and 281, those were like increments. So I think the scale of the program I was using could only hear the sound in those increments. But it's a really great app. I can't show it to you now, but it's I'll put the link in the description. The app that helps me get this is amazing. You can hit an object or like play a guitar note and it'll tell you exactly how many decibels and at what frequency. It's really quite amazing. But I was able to dial in on this signature sound inside of there regarding this aluminum pyramid, you know? So, gosh, in my way of thinking, that kind of confirms that this theory's on point. And really, these are all existing equations. The only thing I added was trying to come up with a system of ratios relative to the height of the pyramid. That's where this square root of 6 comes in. And all you're really doing is thinking, when this thing has a shock wave, how does the sound bounce around in here? How many times does it rattle around and get the whole thing to move in some pattern? And so the only way you could guess that would be to just start throwing numbers into it. But numbers that come from here, right? So it's sort of like 4 times the height. But instead of, then I invert this is the part that's tripping me out. I invert the height. So it's kind of like a weird little ratio trick, but it seems to have worked. So I don't know. I mean, I'd like to think I'm on to something here with this stuff. You know, put it in the comments if you think I'm wackadoodle, but the only part of the, I mean, I know, actually, you know, don't say nothing like that. Cause like, psh, you know, I got this, dude. Come on. This shit's real. The only part that I winged it was just these numbers here. So maybe if I'm wrong, somebody can prove it, dude, and come up with a different way of getting that ratio dialed in. You know, that'd be awesome. So if anybody's like, hey, you know, I was looking at your equations and I think you're a shade off. Like, dude, tell me the right one. But I think this is pretty damn close. 12,118, 12,188. I mean, that's pretty close. So I went ahead and took the liberty of calculating the vibrational frequency of the Great Pyramid of Giza based on limestone having a 4,700 meters per second speed of a longitudinal shock wave, and then based on these other numbers here that the height is 146 meters instead of like this is 0.15 or whatever, 0.16 whatever. Oh, and that's another thing. When you cast an equilateral tetrahedron, you can, it doesn't matter if you run out of aluminum, it'll just proportionally shrink it because of the way the angles go. It's kind of neat. It's definitely a great shape for experimenting with. So yeah, back to the Great Pyramid of Giza. Yeah, so the frequency comes out to 8.65 hertz. Well, that's close to this Schumann resonance. And, you know, I didn't even account for those little half a meter in, or whatever, 9/10 of a meter indentions in the center of the Great Pyramid of Giza. So honestly, like, some of these theories about the pyramids are not misplaced. All that being said, it's my opinion that the Great Pyramid of Giza was not designed as an energy emission device or an energy transmission device. No, if anything, it would probably soak up vibrations from the environment because of its mass and its shape. Essentially, a pyramid doesn't like to vibrate that well, although it will have a resonant frequency. So, if anything, you know, the Great Monument, which all historians, you know, from what I've read, they're always like, well, it's just a big tomb. You know, they were obsessed with status in the afterlife, so they made a giant tomb. Well, okay, I'll accept that. But people instinctively know when mysteries are afoot, you know, and that's where I'm like, okay, maybe it does a little something. I'm thinking that the Great Pyramid of Giza perhaps is a, yeah, I think the Great Pyramid of Giza might be some energy absorber, maybe like almost like a canceling out of some other frequency that's floating around. That's the most I can say about it. Totally guesswork, and I hope that my interest in the mystical doesn't like turn people off. I mean, these equations are engineering equations, and this is a real aluminum, and it has a real frequency, and I have real data to prove it. So someone smarter than me, take this idea, bring it down to the molecular level, like a s orbitals. You know about the s orbitals. The chemistry people know it's a spherical shaped orbital of electron cloud. Well, how does a jar of marbles pack? Well, I'll tell you how. The spheres there, the spheres are touching and creating this shape. So it's good to know this equation for figuring wave vibrations between points of the nuclei in an atomic material where there's multiple. But it probably only would be accurate for HCP. From best I can tell, there's an atomic packing factor where you've got different ways the atoms arrange, because they're not all spherical shaped. Like, that's the trick, is some of them have orbitals from vibrational patterns and such, so they don't stack together perfectly all like this, but some will. And for those elements, this equation will help you understand the relationship between the nuclei of atoms in a solid material. So I hope that helps people understand. And I gotta get a popsicle. I gotta cool it down. Have a good evening.